Hello, and welcome back to another Math 104 lecture. So, we have put this off as long as we can possibly put it off. The procrastination has to come to an end at some point. And after all, this class is called College Algebra and Trigonometry. So today we are starting trigonometry. Now, before anybody freaks out, there's not a whole lot that we're covering. In fact, most of trigonometry gets covered in pre-calculus, but with the lectures that we're going to be covering, this is going to give you a good head start into pre-calc and cover a lot of the concepts that you're going to be learning in future math classes. Or if you aren't taking any future math classes, then at the very least this will give you a good foundation for trigonometry in general. So, trigonometry. Trigonometry is essentially the study of angles. It provides, it goes hand in hand with geometry, where geometry, the main focus of it is you're dealing with shapes, and trigonometry is you're dealing with, the angles of those shapes, or the angles in general. So before we actually get started, we should probably discuss the notation for angles and how we're going to be discussing angles from henceforth. So if I draw my standard quadrants here, quadrants 1, 2, 3, and 4, remember we start in the top right and we go counterclockwise, right? If this is quadrant 1, we're going counterclockwise, and so this is 2, 3, and 4 finally. So with angles, angles are the way that we define them is also counterclockwise. We define an angle to be positive if it is going counterclockwise, and we define an angle to be negative if it's going clockwise. Okay, so if I draw an angle, and for the record, we're always generally starting, when we're talking about angles, we're generally starting from the x-axis right here. And so if I draw this angle where, obviously this is a ray. If you've never heard this terminology before, a ray extends from the origin, and it acts as kind of a leg of the angle. And the other piece of the angle is formed, obviously, from the x-axis, just like we just talked about. So if I have this angle, and if you've never seen this symbol before, this is called theta. Now, please, I know my handwriting isn't that great, and I will try to. There we go. That's theta. I will try my best to not confuse you guys, but there is a very, 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 very big difference between theta and also the empty set. Right. Notice, in general, it's going to be smaller. The line isn't going to really extend beyond the circle. But I just want to really hammer in. I know we've talked about the empty set for quite a bit. Empty set, is akin to having no solution, that sort of thing. That's not what we're talking about here. Theta is a letter of the Greek alphabet, and we use theta in general when we're talking about angles. There's one other Greek letter that we also generally use. And in fact, there's a couple, but the most common ones are theta, which one more time is going to look like this, and phi, which looks like that. Okay, so those are the two common ones, and then there's a couple other ones that we use. For example, we use alpha quite a bit, and we also use beta. So these are the most common representations of angles that you'll see, but just for the sake of this class, we're more than likely going to just be sticking with just theta here. So in any event, the reason we know that this angle is going to be positive is because it's going counterclockwise from the x-axis, right? We're starting from the x-axis, it goes counterclockwise from there, and then theta is the angle that's formed after going counterclockwise. So we know theta is positive. If, however, we saw something like this, where the angle formed is still between the x-axis, but now the ray, the other side of the angle, is now in the fourth quadrant, we say that this is a negative angle. So we would know that the theta's measurement would be a negative value here. And finally, there's one last piece of terminology that we need to discuss, and that's called the terminal angle. So terminal angle is where the ray is ending up, essentially. So if we draw a ray as such, without me actually telling you what side the angle is actually being formed on of this ray, you really couldn't tell me, where it's ending, the terminal part of the angle, what's going on. It could be, which I'll draw in red, it could be this, like we just talked about. So theta could be negative, and also it could be this piece right here, right, where the entire, starting from the x-axis going clockwise, it's that entire angle formed. And notice that's almost one full revolution, right? So what we call these angles, when we see here we have the red and the blue, and that makes up essentially one full revolution. We call these angles coterminal. And the reason we call them coterminal is because notice that they're ending on the same ray, which one more time is, and I'm just gonna use my little rainbow pen here to notate this. We're talking about this ray right here that forms the angle. Coterminal angles are where you have two angles that end on the same ray, but notice how one is positive and one is negative. Now, in reality, when we start talking about sine and cosine, and we start discussing things of that nature, trigonometric functions, these values actually produce the exact same thing. It's not going to make a difference whether or not you're using the negative value or the positive value, because notice how the ray that's formed, the terminal ray here, the terminal point, it's connected for both of them. But just for the sake of argument, it is good to understand what makes an angle negative and what makes an angle positive. So just for the sake of argument, again, because I color-coded this, the angle in red would be negative and the angle in blue would be positive, despite them being coterminal. Okay, so there's 4 different kinds of angles, and now we've talked about one of them already. So the first one, which is one that I'm sure everybody knows by now, since we've already discussed it at least a little bit, is a right angle. A right angle, notated by that little box in the corner, is where you have exactly a 90-degree angle. So no more, no less. It is exactly 90 degrees. And one of the special properties about a right angle is that if you have a right angle, then the two lines or line segments that form the right angle are perpendicular. We talked about perpendicular before when we were talking about lines, but our definition prior to this was strictly based on slopes. If you guys remember, just going back when we were talking about slopes of lines and deciding whether or not they were perpendicular, we figured that out by finding the slopes of both lines, so M1 and M2, and if you multiplied them together and got -1, then they were perpendicular, right? Another way to say this is if you solved for 1, that means, moving one of them to the other side, one would be the negative reciprocal of the other. In this case, we can actually forego this definition when we're talking about right angles, just for the purpose of trigonometry. A right angle is now when essentially two lines are perpendicular to each other. Okay? Okay, so the next angle that we have to talk about is acute angles. Acute angles are any angles that are less than 90 degrees. So if, again, I'll do this instead. Sorry, guys. So if I have a right angle, which I'm just going to freehand, so please bear with me. If I have a right angle here, then drawn in red, this would be an acute angle. And the reason we know this is acute in acute angle is because, again, we see that it's starting from the same origin. We see that it is obviously going to be less valued than 90 degrees because the right angle is 90 degrees. So as long as your angle falls below 90 degrees, it's an acute angle. Then we also have obtuse angles. Obtuse angles are any angles that are larger 90 degrees. So if I draw this angle, for example, we can see that this is definitely larger than 90 degrees, so this is obtuse. And last but not least, we talked about right angles, we talked about acute, we talked about obtuse. The last one is a straight angle. So a straight angle is essentially where you have a line. And the way that we think about this is if a right angle is 90 degrees, so if a right angle was essentially this, notice how this is double a right angle. Now we're going to start really talking about degrees and radians in a second here, but you could already kind of infer that if a right angle is 90 degrees, a straight angle should be double that because it is two different right angles. So a straight angle is 180 degrees. Okay, So measurement of angles. Again, I've been using this term degrees. What is a degree? In a circle, when we're discussing, because when we're talking about angles, we know that we can draw an infinite amount of angles starting from the center of a circle. And if we draw our axes here, so just bear with me here, not exactly straight, but it's fine. So if we start from the center of our circle here, we know that we can draw an infinite amount of angles, but as far as how many degrees there are 360 degrees in a circle. So when we're talking about a right angle, notice that a right angle is where we have 90 degrees, which is essentially a quarter of a circle. And then if we're talking about, a straight angle, then that's half a circle, right? That would essentially be this entire piece right here, which would be 180 degrees. And now if you're talking about the entire circle, well, that's two different straight angles. So 2 times 180, and we end up at 360, right? So there are 360 degrees inside of a circle, and there's 360 degrees that we can compose with angles. So if we have a right angle here, then that's 90, and half of that, which is right down the middle, well, this would be a 45-degree angle, and so on and so forth. We can split this up depending on essentially a ratio based off of 90 degrees. So if 90 degrees is, once again, the angle that's formed by two perpendicular lines, and say I wanted to draw 30 degrees. Well, 30 degrees is going to be looking something like this. We know that this is essentially 30 degrees, and how do we figure out how to draw 30 degrees? Well, the way to figure it out is you think of, again, in proportion to 90, right? What is 30? 30 degrees is 90 degrees, but it's a third of it, right? We can think of, again, if we're talking about proportions of sizes here, of angles, then what I have to think about is, okay, well, I'm going to go 90 degrees, but instead of going all the way, I'm only going to go a third of the way. So instead of going this entire way here, I'm just going to go a third of the way, and we see that, again, this lines up, right? To draw a 30-degree angle, you're essentially just going a third of the way of doing a right angle. So just again, to give one more demonstration of this, if I wanted to draw the 45-degree angle, like again I just did earlier, 45 degrees, well, to put that in, proportion to 90, 45 is the same thing as 1/2 of 90. So if, again, I know 90 degrees is, the right angle, then I'm going halfway to 90. So that means I'm going just up to halfway that I normally would, right? So halfway would be just about here. Okay, so we can kind of estimate where or how to draw these angles as long as we keep in the back of our heads how much 90 degrees is and what the angle we're trying to draw, how it, it essentially, the proportion of it to 90. If we can say, okay, well, if 45 is half of 90, then I only need to draw that angle halfway to, drawing a full right angle, and so on and so forth. So what I want you guys to do for your first classwork assignment is I want you to try to draw the following. I want you to try to draw 60 degrees, 225 degrees, -30, and 330. So to write those out, again, I want you to draw 60 degrees, 225, -30, and 330. Okay, so give it a second, try to figure this out. Again, try, before you actually attempt to draw these, try to figure out what they are in proportion to 90 before you, start drawing. Okay, so trying to figure these out one at a time. Let's start with 60. So to do 60, well, again, notice how it's positive, right? This is a positive 60 degrees, so we know for a fact this is going to be counterclockwise when we draw this. So we're talking about this area right here. You know it's going to be within the first quadrant because it's less than 90 degrees, right? Which means it's an acute angle. So if this right here is 90 degrees and 90 degrees makes up the first quadrant, then you know that 60 degrees has to lay somewhere in this general ballpark, right? Okay, so what is 60 in regards to 90? Well, 60 degrees, if we're trying to compare it to 90, is if we went 2/3 of the way to 90 degrees. So once again, 90 degrees is if we went all the way from the x-axis, made an angle, to the top of the y-axis, right? So 60 degrees is if I went 2/3 of that way. If I said, okay, I'm going to go 2/3 of the way, but then stop. So 60 degrees is essentially going to look something like that. And so we could say, yeah, this is a reasonable expectation of what 60 degrees would look like. Okay. Next up, we have 225. So the hard part really comes in with trying to figure out how these angles match up and where you should expect to draw them. So 225, we have to think about this. How much is 225 compared to what we know? Well, we know that this here at the top is 90 degrees, right? And we just talked about straight angles, and a straight angle is essentially two 90 degrees in a row. So we have first we go 90, and then we go another 90, and we end up at 180, right? Well, what happens if we go another another 90? Well, that makes this 270 degrees. And just like we talked about, there are 360 degrees total. We started from 0, and when you go one full rotation, you've gone 360 degrees. So we know that 225 falls somewhere between 180 and 270. So when we're trying to draw this 225, we should be looking at the third quadrant. We know it's going to be somewhere around here. So we just have to figure out, okay, well, where is it? Now, when we're comparing it to 180 or 270, either way, you can ask yourself, okay, well, what's the difference between the two? This is also another good idea. Instead of just comparing it to 90, I'm not going to do that because 225 is far beyond 90 degrees, right? 90 degrees is over here. I don't want to compare it to that because I know it's not going to lie in quadrant 1 or 2. But I know because it's going to lie in quadrant 3, I can compare it to 180 or 270 and see what this is going to come out with, right? So if I compare it to 180 degrees, sorry, missed the degrees there, then we just have to figure out, okay, well, how many more degrees is it than 180? So this is another good way that you can figure this out. So if we say, okay, well, 225 degrees minus 180 degrees, what should this give us? Well, this gives us 45 degrees, which says this is 45 degrees more than 180. And we already learned before what 45 degrees looks like, right? 45 degrees is essentially just splitting the quadrant in half. But it's not 45 degrees, it's 225, right? It's 180 and then an additional 45 degrees. So we went all the way to 180 and then we went 45 more degrees. So this would make it 45 more degrees. And so we split this quadrant in half. And now we see, oh yeah, the entire angle this makes is 225 degrees. Okay, again, the idea is just comparing it to the pieces that make up the quadrants. And that way you can figure out where this lies. If this were 271 degrees, it's more than 270, so 271 would fall somewhere over here. And because it's much closer to 270 than it is to 360, you know how you could, accurately draw this. 271 would essentially look something like this, right? Where 271 is just slightly more than 270, far closer to 270 than it is to 360, but not exactly 270. So for 225, once again, we figured out that it was 45 degrees more than 180, and because we know how to draw a 45-degree angle, this really isn't too much of a problem, right? We're just splitting the quadrant in half, so we add 45 on top of that 180, and we get our 225 as desired. Okay, so next up, we have negative 30. So negative 30, again, we were already talking about the signs of angles, right? So if I'm given negative 30 degrees, I know for fact that I'm talking about going clockwise. The negative sign implies that I'm flipping the orientation here. Instead of going counterclockwise with my angles, now I'm going clockwise with my angle because it's, again, negative 30. So if we're talking about negative signs, we're still starting from 0. And again, if we're talking about negatives, that would make this negative 90, right? I've gone 90 degrees. This is still a right angle, but, I haven't, you're used to seeing 90 degrees up here, and this is all totally still fine to draw it this way. It's just, a different way of thinking, right? We just talked about this being 270 degrees, but when we're talking about going clockwise, we can just call this negative 90. Okay, so it's the same thing. It really won't matter. It's just a different way of thinking because, again, our sign is negative now. So we're going, again, negative 30 degrees. And now we know it's less than negative 90, so it's going to be somewhere in this quadrant. And as a result, we just need to figure out, again, proportions, right? It's not going to be straight down the middle because this would be negative 45 degrees. So we know it's going to lean a little bit closer to 0 than it is to negative 90. And if we're talking about proportions, negative 30 is 1/3 of negative 90, right? So we know that it's effectively just 1/3 of the way, which would make it somewhere about here. So this angle right here would be negative 30 degrees. And last but not least, we have to do 330 degrees. So to do 330 degrees, once again, we see that it's a positive number. If this is 90, this is 180, and this is 270. And because we're looking for 330 degrees, again, we know it's going to be more than 270, right? If we go one full revolution, then we've gone 360. But so we know it's going to be somewhere over here. Well, 330, if I know it lays pretty close to 360, we can compare it and we can see how far away, how many degrees it is away from 360. So 360 minus 330 gives me 30 degrees. So we know that there's going to be a difference of 30 degrees between where 330 ends up and where 360 is, right? So we know that it's effectively going to be this line here. And so we have now made this angle 330 degrees. But you might say, well, wait, isn't this the exact same angle that we just had with negative 30? And yes, this angle right here, now that I'm drawing in red, is in fact negative 30 degrees. And now we go back to that terminology that I referenced before, which is coterminal. Notice how 330 and negative 30 degrees are ending on the same ray. However, one is positive and one is negative, right? We call these coterminal angles. So this is a good example of seeing that definition in practice. Okay, so that was kind of a brief conception of degrees. So now we also have to talk about the other unit of measurement. So when we're talking about angles, we freely go back and forth between degrees and also what are known as radians. So a radian, when we're talking about a circle or when we're talking about angles, one full revolution starting from, again, if this is 0, one full revolution is said to be 2 pi radians. Okay, so if that's the case, what you can infer then is that half of a revolution, so just going halfway around, then that would make this pi. And well, if we're talking about a quarter of a revolution, we split this in 2 again, this would be pi over 2, and this is 3 pi over 2. And again, 2 pi is going the entire way around. So radians, again, we generally use pi when we're talking about the amount of revolutions or rotations that we've gone around. And this is how we split it up. So pi over 2, you're used to seeing it, as we just discussed, as 90 degrees. Well, how are we getting pi over 2? What is the conversion between degrees and radians? So the conversion is as follows. If we're given some angle in degrees, you convert it to radians by taking your angle and multiplying it by pi over 180. And this will give you your answer in radians. Okay, so let's do a couple quick examples. Let's try doing 90 degrees. So 90 degrees, again, what we're going to do is we're going to plug in our 90 degrees. Again, we plug in 90 for our angle and multiply it by pi over 180. And how does it simplify? Well, 90 over 180 should just be a half, right? 90 divided by 180 is a half. The same, 9 over 18 is a half, right? So we get 1/2 pi radians. And you can always freely move when you're multiplying a fraction times a number. You can always move that number to the numerator. So it's the same thing as pi over 2 radians, which is exactly what we have, right? 90 degrees, pi over 2 radians. And we can convert as such, right? So let's do one more example just with that conversion rate. Again, where the conversion is whatever your angle is in degrees, it's the same thing as that same angle times pi over 180, and you'll get your answer in radians. So one more time, let's do this with negative 135. So let's say we have negative 135. So that means we have negative 135 pi over 180. And to simplify this down, all you have to do is just try to simplify 135 over 180, which, might seem a little tedious, but that's okay. What we're going to do is we're just going to factor things down, see what we can pull out of both, and just start canceling, right? We know that we can pull a 5 out of both of these terms, right? 180 is divisible by 5. 135 is very clearly divisible by 5. So we're going to pull a 5 out of both. So pulling a 5 out, what does that leave us with? 135 divided by 5. And at this point, I wouldn't blame you if you tried using a calculator, but you don't have to. Remember, you can always factor based off of the largest numbers. You can decompose 135 is what I'm saying. So if we have 135, you can try factoring 100 first, which leaves you with 20, and then 35, which leaves you with 7. So this is the same thing as 5 times negative 27. If you didn't really understand what I just did right there, that's okay. Just, try your best to factor so that way you can get good at trying to break up these numbers and reduce them. But if you need a calculator, you need a calculator, and that's okay. So we're going to do the same thing with 180. Again, we're going to do the breaking up by 5. So this is 5, and the other factor here is 36. If you're wondering where I got 36 from, 180 divided by 10 is 18, right? But we're trying to break it up by 5, not by 10. So multiply back by 2 because we divided by 10, not 5. So 18 times 2 gives me 36. And again, if I lost you there, no worries. Just try to break up 180 and you'll get the same thing that I got. Okay, so now we see, oh yeah, we can cancel out the 5, right? And we can actually break this up a little bit more. We see 27 is divisible by 3. 36 is definitely divisible by 3. So breaking this up a little bit more, we can take out a 3. So we have 3, and what happens when I take this out? That leaves me with negative 9 pi. And taking a 3 out of 36, that leaves me with 3 times 12. And oh yeah, we're reducing this slowly but surely, but it's definitely something that we could have done a little bit faster. And now we see we have 9 and 12. So one more time should do it. We're going to take out a 3 one more time. So taking out a 3, this leaves me with 3 and negative 3 pi over 3 times 4. And so when we finally are all said and done with reducing this, we're left with negative 3 pi over 4 radians. And this is now in its complete form. So we can see that negative 135 degrees simplifies down to be negative 3 pi over 4 radians. And that's all it is. Again, the idea here is you just remember your conversion, right? Your conversion is whatever your angle is in degrees, you're multiplying it by pi over 180 to get radians. So that's exactly what we did here. And through a series of cancellations and factoring, we saw that, oh yeah, we can just simplify it down to be this pretty simple fraction. Okay, so with all that being said, I'd like you guys to go ahead and try the second classwork where you guys convert some degrees to radians. Okay, so as follows, convert 45 degrees, 60 degrees, and negative 225 degrees, all 3 of those to radians, and see what you can come up with. Unpause the video when you are ready. Okay, so once again, what you should keep in mind is whatever theta, whatever angle you start with in degrees, it's the same thing as taking that angle, multiplying it by pi over 180, and that's how you get it to radians, right? So for 45, we're going to start with 45 here. 45 is, starting in degrees, it's just 45 degrees, and this is equal to 45 pi over 180. I'm going to skip essentially all the steps that I did before when I was, going through each single factor and canceling each single factor, but hopefully you guys are going to get okay at reducing fractions. So this is the same thing as 45 pi over 4 times 45. And we see here that the 45s are going to cancel out, right? So when they cancel out, we are just left with pi over 4 radians. So pi over 4 radians. And now, just to double check your work, if you really, want to make sure that we're good to go, remember that we already solved for 90 degrees, right? We solved that 90 degrees earlier is the same thing as pi over 2 radians. Well, 45 degrees is half of 90, right? So you would imagine the conversion would still hold. If 45 degrees is half of 90, then the radians should also be halved. So if pi over 2 is equivalent to 90 degrees, then divide that by 2, and you should get 45 degrees, but in radians. So pi over 2 divided by 2 should just give you pi over 4, which is exactly what we get. Okay, so that's a good way for you to check for yourself that you're actually still on the same page, that you're not getting these ridiculous answers. So we got 45 degrees is equal to pi over 4 radians. Next up, we have to do the 60 degrees. So doing 60 degrees, this is going to be, again, 60 pi over 180 rad. Hopefully this one is not too bad. You guys could see it fairly immediately. 60 over 180, you first cancel out 10, so then you're just left with 6 over 18. And yeah, that's just going to leave you with pi over 3 radians. Okay, and last but not least, we have negative 225 degrees. So negative 225 degrees. What this should give you is negative 225 pi all over 180. And at this point, I would expect you guys to take a little bit of time to try to figure this one out in terms of breaking it apart. But we already talked about how 225 is 45 degrees past 180, right? And 45 degrees actually goes into 180 evenly. So we can see that 225, one of its factors is 45 degrees, and a factor of 180, as I just said, is also 45 degrees. So when we factor this up and we break it up, we see that it's negative 5 times 45 degrees pi all over 4 times 45. And sorry, I said 45 degrees pi. I just meant 45. My mistake. And when we do some cancellations, we see that we're just going to be left with negative 5 over 4, or negative 5 pi over 4. You can leave the pi on the outside, but most of the time for our common convention is we put the pi up in the numerator. So negative 5 pi over 4 is going to be your final answer here. Okay, the important part here is understanding your conversion. Your conversion from degrees to radians is, if you're going from degrees to radians, you are multiplying by pi over 180. So with that being said, we can actually go the opposite direction, right? If I give you an angle in terms of radians, you can take that angle and turn it into degrees so you have a better idea of what you're looking at. And so if we're starting with our conversion, again, just rewriting this one more time. If I want to solve for my angle in terms of radians, and if I essentially what that's allowing me to do is have radians by itself, I'm just going to isolate for my theta over here, right? So what that means is I'm going to move the 180 over, so multiply both sides by 180. So we have 180 and, oops, we have 180, and then we're going to divide by pi here. So dividing by pi, and this should just leave me with my angle in terms of radians. So now what we see here is the dichotomy between radians and degrees is essentially just multiplying by either pi over 180 to get radians, or if you're given radians, you're multiplying by 180 over pi. And that's it. That's really realistically all you're doing. If you're going in this direction, you multiply by pi over 180. If you're going in this direction, you multiply by 180 over pi. And that's all she wrote. So just to do some really quick examples of this, converting, again, radians to degrees, let's say that we have pi over 3 radians. So just let me clear this off. So if I gave you pi over 3 radians, and I wanted to convert this to degrees, well, again, our conversion is, okay, we have pi over 3 rad. Now what I'm going to do is I'm going to take this piece and I'm going to multiply it by 180 over pi, right? So this should essentially give me the same thing. So I should have pi over 3 times 180 divided by pi, and this will be in terms of degrees now, right? So I'm just going to put the little degree symbol up there. And when I simplify this down, 180, divided by 3 should give me 60. So we end up with 60 pi divided by pi, and we see that the pi's cancel out, and so we are just left with 60 degrees. So pi over 3 radians converts back to 60 degrees just by taking your pi over 3 and multiplying it by 180 over pi. Okay, and just to do one more example, because I'm not going to make you guys do a classwork example on this, one more example of this is if I gave you, let's say, negative 2 pi over 9, right? So if we have negative 2 pi over 9, the conversion from radians to degrees is we multiply by 180 over pi, right? So that means we're going to have 2 pi over 9, well, negative 2 pi over 9 times 180 all over pi. And this is now going to be in terms of degrees. So when I do some simplifications here, 180 divided by 9, that's probably the first thing that you're going to want to do here, right? The 180 divided by 9, that's going to give me 20. So now what I have is negative 2 pi times 20 all over pi. And again, we're keeping that degree symbol there. We see that the pi's are going to cancel out, and we're just going to have negative 2 times 20, which leaves me with negative 40 degrees. And once again, we're done, right? So we see that negative 2 pi over 9 radians converts to negative 40 degrees. And this is a really important concept. Notice how the negative sign sticks throughout, right? The negative isn't going away, which is indicative of it saying, okay, whether or not you're in radians or degrees, if you're going clockwise, you're going clockwise. If you're going counterclockwise, you're still going counterclockwise. Converting between radians and degrees doesn't change the direction that the angle is going, okay? Okay, so with all that being said, let's talk about concepts of complementary angles and supplementary angles. So if we're talking about complementary angles, these are going to be two angles that when they add together are going to give you 90 degrees. So complementary are two angles whose sum is 90 degrees. Another way to think about this is two angles whose sum is pi over 2 radians. So I'll just put pi over 2 radians. In general, when we're talking about complementary and supplementary, we are talking about degrees, but it's not uncommon to see it in radians. So just familiarize yourself with pi over 2 and also what's coming, which is pi. Okay, so that's complementary. And supplementary angles are two angles whose sum is 180 degrees, and again, or just pi radians. Again, remember that pi radians is equal to 180 degrees. Pi over 2 radians is 90 degrees. So let's just see this in action real quick. If I said, for example, find the complement to 37 degrees, how would you handle this? Find the complement, which I'm abbreviating, to 37 degrees. How do we handle this? Well, we know that we're talking about a sum of two angles, right? When we're talking about complementary or supplementary, either way, the key word is it's a sum of two angles. So you know it's two angles being added together. So if I say find the complement to 37 degrees, we know there's some other angle, which I'm going to call theta, to where when I add these together, it should give me 90 degrees. So, okay. That's easy enough. Now we just solve for theta, right? So subtract 37 on both sides, and what you're left with is just going to be 53 degrees, right? All I did is I set this up to be equal to 90 degrees because it says find the complement. If it said find the supplement, then I would set it equal to 180 degrees. But again, that's just the terminology you have to understand. Complementary is indicative of 90 degrees. Supplementary is indicative of 180 degrees. So when it says find the complement, it's just saying, yeah, sure, find the other angle that when you add to it gives you 90. Another, like a good visualization of this is if we're talking about a right angle here, right? So this is supposed to be a 90-degree angle. Say we have some angle here, and I don't know what it is, right? Or even better, just sticking with the example, we can say this is 37 degrees. Then there's some other angle that exists, which I'll highlight in blue here. There's this angle that exists, which I'm calling theta, that when you add it to the 37, you should get a right angle. Okay, so that's the visualization for complementary, is that you just have two acute angles that when added together, sum to be 90. So one of them, if one of them exists, then the other one also exists. Okay, now next up is what I want to do is I want to find the complement again to, I'm sorry, I want to find the supplement to 104 degrees. So one more time, if I say find the supplement, to 104 degrees, the idea here is, again, there's going to be, and if I just give you guys a visualization, let's say that, this here is 104 degrees. Well, that means that there's some other angle that exists right here that when I add it to 104 should give me a total of a straight angle, which is 180. So supplement is saying, okay, find that other angle to where when you add them together, it gives you 180. So, okay, sure. So we have 104 plus theta is equal to 180. And, obviously you can write the degrees here. We know it's in degrees because, it's out of 180. That's okay. So we're just going to subtract 104 from both sides, and subtracting 104 from both sides leaves me with 76 degrees. So we know theta is 76. Okay, not too bad. Again, definitely not outside of the scheme that we've been working with. Let's try one more, but now just with radians, just again to really familiarize ourselves with how to handle this. So if I said find the complement, and again in radians, to the following, so find the complement to 2 pi over 7. 2 pi over 7. Okay, so how do you handle this? Well, again, the idea is you have to understand the terminology. Complementary means two angles that when added together give you 90 degrees. But we're talking about radians, so it's not degrees anymore. Instead of 90 degrees, it's to give you pi over 2 radians. So we still set this up the same way, 2 pi over 7 plus some angle, which, again, angle theta. I'm trying my best to not make it look like the empty set. So 2 pi over 7 plus theta is going to give us pi over 2. Okay, that's not so bad. So how do we solve for this? Well, we solve for this the same way we solve for any unknown variable in any of the lectures that we've done before. We've always isolated it, right? So if I have 2 pi over 7 being added to this angle, what I'm going to do is I'm going to subtract both sides by the 2 pi over 7. So that's going to leave me with theta is equal to pi over 2 minus 2 pi over 7. And how do we subtract fractions? Well, we need a common denominator, right? If we don't have a common denominator, we can't subtract fractions, which means we can't simplify it. So to get a common denominator here, theta is equal to, well, we see we have a 7, we have a 2, so common denominator is probably just going to be 14 here. So that means I'm going to make this 7 pi over 14. Again, multiply top and bottom by 7. And for this one, I'm going to multiply top and bottom by 2. So that should give me 4 pi over 14. And now that I have common denominators, we can just subtract the numerators, which means 7 pi minus 4 pi over 14. And that gives me 3 pi over 14. So we now have our final answer in radians, which is 3 pi over 14. Okay, so that's complementary and supplementary, a crash course on it. Just please be aware that when we're talking about complementary and supplementary, we're talking about two positive angles. We're not talking about negative angles that could possibly, when you do full rotations because of, how coterminal angles work, that might give you a complementary or supplementary angle. Both angles have to be positive when we're discussing complementary and supplementary. Okay, so just keep that in the back of your head. Okay, let's see here. why don't we finish up with one quick thing here? So what I want to do is I want to, again, bring this back to circles, okay? So let's say we have a circle. Pretend it's a circle. Anyway, let me try it one more time. That's a little better. Okay, so let's say we have a circle, and we have the center of the circle marked accordingly, right? That's the very center of the circle. We call any angle formed at the center of the circle a central angle, which, sure, that's not too bad, right? So what I can do here is we can find the arc of a circle. If I have, so we know that from the center of a circle to any point on the circle, we call this the radius, right? If I have an angle formed by any two radii of a circle, so we'll say there, and we'll make another radius right here, and now we have this angle, right? And again, this is just a central angle of a circle. We can figure out the arc of a circle, which we're going to call S. So the arc of the circle is the arc that's being intercepted by the angle. So notice how we have the endpoint here of the two radiuses. The length of S, or the length of the arc of the circle, is figured out by the following. We actually have a formula for this. So S is equal to R times theta. That's it. It's that easy. It's you take your radius, you multiply it by your angle, and the resulting, number that you get is the length of your arc. Okay. There is one caveat to this though. Okay. The caveat is it has to be in radians. Your angle here has to be in radians, which means if I give you an angle in degrees, before you can use this formula, you have to convert it to radians first. Okay, if you try plugging in degrees into this formula, it's not going to work out. You're going to get gibberish. It's going to be a mess. Okay, so convert it to radians first, and only then when it's in radians can you use this formula and figure out the arc of a circle. Okay, so let's try a quick example of this, and we'll see how it comes into effect. Let's say a circle has a radius of 2 meters. So one more time with my circle, my awfully drawn circle. Let's say we have a radius of 2 meters here, right? And what I want to do is I want to find the length of the arc intercepted by a central angle of 225 degrees. So 225 degrees. Again, that's basically going to look something like this, right? And so 225 degrees, we're talking about here, and again, this is also 2, we're talking about this larger angle, right? We're not talking about, because again, this is 225 degrees, we're not talking about the smaller angle, the coterminal angle that's formed here, which I've just drawn in red. We're talking about the larger angle, which was just illustrated, right? So we have to figure out what S is, and S is going to be this entire gigantic piece starting from here that goes all the way around to here, right? Okay, so to do this, again, what we have to do is first we have to convert that 225 degrees to radians. Before we can do anything, before we can apply our formula, and again, our formula is S is equal to R times theta, right? Before we can apply this, we have to convert 225. So 225 degrees. Well, we know how to convert degrees to radians. What we do is we multiply by pi over 180, right? So 225 times pi over 180, and this will give us our answer in radians. And what does this give us? Well, this is 225 over 180, and can't forget the pi. When we simplify this down, we already talked about how this effectively simplifies down because 45 degrees is a factor of both. You can cancel out 45 degrees, or I'm sorry, 45 out of both of them. So this leaves you with 5 pi over 4, right? So now we have 5 pi over 4, which is in terms of radians. We can take this and plug it into our theta now. And we know what R is. R is just 2, right? Our radius is 2. So we have S is equal to 2 times 5 pi over 4. And simplifying this down, this is the same thing as 5 pi over 2, right? If we have a 2 up top and a division of 4, we can cancel out one of the 2's in the bottom. So we have 5 pi over 2. And if you were to plug this into a calculator, which is, something, if once you get to this form, this is probably the best that you can do. But if you were to plug it into a calculator, this is approximately, because remember, pi is an irrational number, this is approximately 7.85 meters. Okay, so notice how the radius is 2 meters, and we're able to figure out the total length of this arc right here just based off of having the radius and the angle, which we again first converted to radians. Okay, and last thing that I want to talk about here today, just so we don't get too bogged down in the details, let's also talk about area of a sector of a circle. So one more time here, we're going to start with a circle. So we have a circle here. We're starting from the center of it, and we're talking about a central angle, right? So I'm going to draw the exact same things that I had before. This is the radius, and I have the angle that's being formed between the two radii, right? And again, we already discussed how we can figure out the arc, right? The arc of the circle is S, and we had the formula S is equal to R times theta, or theta times R. But what I want to talk about now is the area of this angle. So this piece right here that gets formed when we have this central angle. And what I'm going to call this is I'm going to call this area A. We have a formula for this as well. And the formula is as follows. If we're trying to figure out the area of the sector of a circle, well, A is equal to 1/2 R squared times theta. Okay, so notice the differences, right? If we're just talking about the length of some arc, you can just take your radius, multiply it against your angle in radians, and you're done, right? For the area, again, notice the difference. It's R being squared, so it's R times R. It's 1/2 of it, and then also multiply it against the angle, okay? Keep in mind, still needs to be in radians for both of these. You can't have it in degrees for either of them, okay? So if you're given degrees, convert it to radians first, and only then can you find the area of, that of the sector that is being created from the central angle. Also, I do want to just keep in, I do want to point this out. If you're given a circle and you're given any angle formed inside the circle, so an inscribed angle that is not from the center of the circle. So if we're just talking about, let's say, this point right here, and you did something like this would not work. This formula that we have is not going to work out. The reason it doesn't work out is because, again, this is dependent very much on the radius, right? Where radius is determined by the length away from the center of a circle. This is not going to be from the center, and so this is not dependent. These are not going to be your radius. Okay? All right. So I just wanted to point that out, that you can't just pick any random angle. It has to be a central angle of a circle. Okay, so let's close this up with one last example and one last classwork, and we'll call it a day here. So what I want to do is I want to find the area of a circle with the radius of 10 centimeters formed by 60 degrees. So formed by an angle of 60 degrees. Instead of clearing everything, let's just erase that. So again, find the area where your radius is 10 centimeters. So radius is 10 centimeters, and it's formed by the angle of 60 degrees. Okay, so first things first, before we can apply our formula, which one more time is A is equal to 1/2 R squared times theta, before we can apply this, we have to change the degrees to radians, right? So to do that, I want to multiply by 60. I want to multiply by pi over 180. So this is 60 times pi over 180. And 60 over 180, we know, just simplifies down to be a third. So we have pi over 3 radians. Great. We have theta, or our angle, in terms of radians now. That's perfect. Okay. So now what we can do is we can plug this in. So we have A is equal to 1/2 R squared. Well, R was given to us, right? That's 10 centimeters. So 10 squared. We'll worry about the the minutia of the indexes later. So don't worry about the units right now. Just deal with the actual mathematics. So 1/2 times 10 squared times the pi over 3, right? So times pi over 3. Let's go ahead and simplify this. 10 squared is 100 divided by 2, or times 1/2, however you want to think about it, is 50. So we have 50 times pi over 3. And when we get that, there's really no simplifying this down. You get 50 pi over 3. And this is going to be approximately 52.36. And because you had centimeters being squared, your unit of measurement is just centimeters squared, which is exactly what you would expect to get from for an area, is whatever unit you're talking about, that unit squared. But don't worry about the unit of measurement. This isn't a physics class. I'm not too worried about this. What I am mainly worried about is, first off, your conversion of degrees to radians, and secondly, plugging in appropriately, right? Make sure you're plugging in the appropriate number for your radius, and you're plugging in the appropriate value for your angle. So we figured out pi over 3 is our angle in terms of radians. 10 is our unit of measurement here for, or I'm sorry, 10 is our measurement for radius. So 1/2 times 10 squared times pi over 3. And so we get 50 pi over 3, which is about 52, give or take, just a little bit more. Okay. Okay. So with all of that being said, I want you guys to work on your last classwork assignment. So the last classwork assignment is as follows. I want you to find the radius of a circle. So again, keep in mind that we're finding the radius. Find the radius of a circle if the area of a sector is 18 pi meters squared. So don't worry about the unit of measurement. I know I wrote that out as meters squared. I don't want you to think it's 18 pi squared. So you just think about it as 18 pi. Okay, so to repeat myself, find the radius of a circle if the area of a sector is 18 pi and the angle is 45 degrees. Okay, so give it a shot, see what you guys come up with, and we'll take it from there. Okay. So what are we starting with? Just to provide a visual here, we're starting with a circle, right? We know we have some central angle, and we know the angle is 45 degrees, right? So if I were to start like this, we know it's 45 degrees. So this would be 45 degrees. And the area of this entire sector is going to be 18 pi. So this in here is 18 pi. We know, or I'm sorry, we don't know the radius, so we don't know what r is, but that's okay. Let's set up everything and see if we can figure this out, right? So we have a is equal to 1/2 r squared times theta. Well, before we can continue, notice that our theta is still in degrees, right? So we have to convert 45 degrees to radians first. So 45 degrees, we multiply it by pi over 180. So we have 45 pi over 180. We already talked about how 45 goes into 180 cleanly. So this is pi over 4. So now we have pi over 4 radians, which is exactly what we need to be able to plug things in. So we have a, but a is given to us, right? We were given the area, so that's 18 pi is equal to 1/2. We don't know what r is, so we just leave it as r squared. We're trying to find r, trying to find the radius, times pi over 4. Okay, so now what we're going to do is, well, we're trying to figure out what r is, so we're just going to, isolate for r. So what that means is let's simplify the right-hand side first. So we have 18 pi is equal to pi over 4 times 1/2 is the same thing as pi over 8, and we have this r squared. So I'm going to multiply both sides by my, I'm going to multiply both sides by 8, and then I'm going to divide both sides by my pi. So we can take care of the pi first. If I'm dividing both sides by pi, the pi's just cross out, right? So the pi's are gone. And now to multiply both sides by 8, well, what's, 8 times 10 is going to give me 80, and then 8 times 8 is 64. So 80 and 64 is 144, is equal to r squared. And again, if you need a calculator for this, totally fine. Just take care of it. 8 times 18, figure it out, right? And you can also 8 times 18, you do 8 times 8, which is, again, 64, right? And then 8 times 10, and that gives you 80. And you add things up, right? 4 144. But if, you know, this is still too much, just use a calculator. It is what it is. I'm not too, you know, bogged down in those details. This is an online course. I can't stop you from using a calculator. So we have 18 pi, I'm sorry, we have 144 is equal to r squared. And now to just find r, take the square root of both sides, right? We are trying to find r, it's being squared, take the square root. So taking the square root of both sides, we see that square root and the square are going to cancel out, and we are just left with r is equal to 12. Now, here's the question of the day. Is it plus or minus 12? Yes or no? I hope all of you said no. The reason it's not plus or minus is r is a radius. Radius is a length, right? Distance or length cannot be negative. So we are purely talking about positive 12 here. R is 12, not negative 12, just 12. Okay, so we figured out the radius, and the radius is 12, and that's all she wrote. Okay, so try your hand at the homework, see what you guys come up with, and let me know how it goes. Enjoy the rest of your day, evening, night, morning, and I will talk to you next time. Have a good one, guys.